Welcome back to Honors Calculus. In this video, we're going to continue our discussion of analyzing graphs with the idea of end behavior. Formally speaking, we're going to refer to end behavior as a limit, this time the limit at infinity, but this describes the general trend of what a function is doing beyond the point where the graph is interesting. So let's get my head out of the way and start giving some clear definitions on this. That's not a pen, that's a pen. Right. So the limit as x tends towards infinity of f of x is equal to L if and only if for all epsilon greater than 0, there exists some m in the real numbers so that whenever x is greater than m, the absolute value of f of x minus L is less than epsilon. So I kind of think of this in terms of the general rule of limits that we've talked about before. Remember, in general, the limit as x approaches c of f of x is equal to L if and only if for all epsilon greater than 0, there exists some delta greater than 0, such that when the absolute value of x minus c is less than delta, the absolute value of f of x minus L is less than epsilon. So instead of finding a delta greater than 0, and instead of restricting to absolute value x minus c is less than delta, we're now finding any real number m and finding x is greater than m. Well, that makes some sense because if instead of c we're dealing with infinity, that would give us x minus infinity is less than delta. And how do you deal with x minus infinity? Anything minus infinity is negative infinity. So what we're getting here is infinity is less than delta, which makes no sense. So we need some other way of approaching the situation. What we're looking for is x gets bigger and bigger and bigger and bigger. So we can find some big number and only look at things bigger than that. So when we're looking at this m in the real numbers, think about that as some large number, like 10 million, 100 trillion, something ludicrously large, 10 to the 256. And whenever x is bigger than this ridiculously large number, we have our end behavior happening. And the reason that we are interested in limits as x goes to infinity is that whenever this limit exists, the graph will have the behavior of a horizontal asymptote. And for the most part, we're going to assume that limits as x go to infinity are going to follow the same behavior as every other limit. The definition looks so similar that that seems like a reasonable thing to do. And so if we can find a couple of simple cases of how to deal with limits at infinity, then we should be able to use the rules of limits in order to evaluate more general functions. But I'm getting ahead of myself because before I do that, I must also define the limit as x goes to negative infinity, which looks almost exactly the same as the limit as x goes to positive infinity. Except instead of having x greater than m, we're now going to have x less than m. And negative infinity, limits as x goes to negative infinity, produce horizontal asymptotes the same way limits as x goes to positive infinity do. But there are three rules for dealing with limits, and I'm going to look at the rules for positive and for negative infinity, although I'm only going to prove the case of one of them. The first one is a constant. The limit as x goes to infinity of some constant k is equal to that k, and the limit as x goes to negative infinity of some constant k is equal to that k. The limit as x goes to infinity of x raised to the n power, and I'm going to assume that n is a positive integer. Right? So for a positive integer n, the limit as x goes to infinity of x to the n goes to infinity. And the limit as x goes to negative infinity of x to the n, well, this one gets a little bit tricky. It's going to go to positive infinity if n is even. It's going to go to negative infinity if n is odd. So when you have powers, x raised to some positive power, the function is going to head towards infinity. It's going to be unpleasant and not very useful. So that takes us to the useful case. Again, we're going to assume that n is greater than 0. It's a positive integer, although any positive number will work. The limit as x goes to infinity of 1 over x to the n power is equal to 0. And the limit as x goes to negative infinity of 1 over x to the n power is also 0. These are the interesting cases. And this one is the one that I'm going to work through the proof on. Although to make life easy, I'm just going to look at the simplest case of x to the first power and assume that the power rule still works. The limit of something raised to a power is the limit on the base raised to the power after you're done. All right. The definition of the limit tells us to start by letting epsilon be greater than 0. So we let epsilon be greater than 0. And just like the limits we've dealt with previously, next we're going to go off to the side. And we're going to start looking at the absolute value of f of x minus L. Right? We know we want this to be less than epsilon. We haven't proven that. That's what we want. And if we play around with that a little bit, f of x is 1 over x, L is 0. Which means that x, our 1 over x is somewhere between negative epsilon and epsilon. And so, taking the reciprocal here, we get that x is either less than negative 1 over epsilon, or x is greater than positive 1 over epsilon. For the case as x goes to positive infinity, this is going to be the useful branch. For the case of x goes to negative infinity, the other one would be the useful branch. All right, so that's our scratch work. That's our aside. Coming back into the proof, let's assume that x is greater than 1 over epsilon. And because x is greater than 1 over epsilon, we can work backwards through this whole idea. That means that 1 over x must be less than epsilon. And taking the absolute value, because I know that epsilon is greater than 0, that means that x has to be positive. So if I take the absolute value, I'm sorry, I'm getting a little bit ahead of myself. I know that epsilon is greater than 0, which means that 1 over epsilon is greater than 0. So x is greater than 0, which means that 1 over x is greater than 0. So I know that it is also going to be the case that the absolute value of 1 over x is less than epsilon. And because of that, the absolute value of 1 over x minus 0 is less than epsilon, which is exactly what we wanted to show as the definition of this limit. So 1 over x goes to 0 as x goes to infinity. And that's essentially our entire goal in working with these limits. If we can find a way to rearrange so that we have a bunch of 1 over x's, they will all go to 0. So if I want to take the limit as x goes to infinity of 5 minus 3 over x squared, using properties of limits, again, I haven't proven them, but I'm going to assume that all of the properties we've talked about before still work. We can split this up and take the limit as x goes to infinity of 5 minus 3 times the limit as x goes to infinity of 1 over x squared. But we can even split that up and separately look at the limit as x goes to infinity of 5 minus 3 times the limit as x goes to infinity of 1 over x, that whole thing squared, right? The limit of a power is the power of the limit. And the limit as x goes to infinity of 5 is 5. And then we have 3 times limit as x goes to infinity of 1 over x is 0. That whole thing is squared. 0 squared is 0, 3 times 0 is 0, and we are left with simply 5. Looking at one more, if I want to take the limit as x goes to infinity of 7x squared plus 9x minus 6 over x cubed. Now, let's make that x squared plus 5x plus 4. Right? 7x squared plus 9x minus 6 over x squared plus 5x minus 4. Here, I'm going to use the other property of limits, the thing that we used quite a bit of in evaluating limits earlier, and that is assuming that I can simply move things around in the fraction and not worry about dividing by 0 or any issues or solving that. In this case, I'm going to multiply numerator and denominator by 1 over x squared. I chose x squared because x squared is the highest power that appears anywhere in this particular expression. Right? It appears more than once, but what's important is it's the highest power on x that appears in either the numerator or denominator. Right? Because that's x squared, I'm going to multiply numerator by 1 over x squared, and I'm going to multiply denominator by 1 over x squared. And distributing that through, this is going to be the limit as x approaches infinity of 7x squared over x squared plus 9x over x squared minus 6, 1 over x squared. And then we have x squared over x squared, 5x over x squared, and 4 times 1 over x squared. And yeah, I'll simplify that. This is the limit as x goes to infinity. X squared divided by x squared is 1, so that's just 7. X over x squared is 1 over x. And then we have an x squared over x squared and an x over x squared in the denominator as well that will also simplify out. Right? The limit of a quotient is the quotient of a limit. The limit of the sum is the sum of the limit. The limit of the product is the product of limits. All those things that we've dealt with before. So I can take limit term by term. I've got a 1 over x. That's going to go to 0. I've got a 1 over x squared. That's going to go to 0. I've got this 1 over x that's going to go to 0. I've got this 1 over x squared that's going to go to 0. And all told, when I take the limit, I'm going to get 7 plus 9 times 0 minus 6 times 0 over 1 plus 5 times 0 minus 4 times 0, which is 7 over 1, or just 7. Here's one for you to take a look at. The limit as x goes to infinity of 3x squared minus 7x plus 6 all over 5x cubed minus 9x squared plus 8x plus 2. Take a few minutes to see where you can get to with this problem, and I'll see you in the next video.